Okay, so we are going to solve the case where the potential energy is a delta function. So we'll be dealing now with the delta function. Well, so the potential energy involves a delta function. And we are going to add to this story a constant in front with that minus sign. So this is the potential energy that we are playing with. Okay. Well, so let's sketch this. Okay, so this is my x-axis, and I'm going to sketch this V there. Let me use, let's see, red. So my potential is 0 everywhere. Now the delta function is 0 everywhere, except right when x is 0, where it becomes infinitely negative, and then it's 0 again on the positive side. Now comes the choice. There are two possibilities for us. Either the energy is negative or the energy is positive. We are going to start solving first the case where the energy is negative. Okay, so this is the case that we'll be dealing with bound states. Why bound states? Remember, the definition is if the energy is smaller than the potential energy at minus infinity, and it is smaller than the potential energy at plus infinity, that gives us bound states. Okay, so we are going to start dealing with this case of bound states. And the first thing that we are going to do is we are going to split the plot that we just drew into two different regions. The region 1 here, which is for x negative, where the potential is 0, and the energy 2 here, or the region 2 here, where the potential energy is also 0. And so let's write Schrödinger's equation, the time-independent Schrödinger's equation, these two regions. Well, let me first write the general equation here. So second order derivative plus the potential. And so this is the equation. Well, for region 1, what is going to be the equation? Well, the potential is 0. So for region 1, this is the equation without the potential, which is 0. And for region 2, same thing. The potential energy is 0 there as well. Okay. And these are the equations that we are going to try to solve. But before we do anything, let's think a little bit about this problem, okay? Even before solving this equation, let's think about what we should expect. So I'm going to put these equations a little below to give us space to think about these two regions, region 1 and region 2. Well, what do we have? Let's start with region 1. What do we see? The energy there, that negative value, is smaller than our potential, because our potential is 0. So if the energy is smaller than the potential energy, if this total energy is smaller than the potential energy, this classically is impossible. So this region is classically forbidden or prohibited, whatever word you want to use. Okay, so this is classically forbidden. Region 2 is the same story. The energy is below the potential. The potential is what we have there in red, and you see the energy is below. So the energy is below, classically forbidden. Classically, there would never be a particle there. And let's remember why. The classically, so this is a parenthesis for things. In classical mechanics, we have the total energy is the kinetic energy plus the potential energy, correct? Now, the kinetic energy is positive. You see P squared there. So it's positive. There is no way the potential could be larger than the energy. The energy classically is always larger than V. Okay, so in this scenario here in our region 1 or in our region 2, well, it would not be allowed classically. It would not exist classically. So if we are in a region that is classically forbidden, okay, we can find a particle there, but the probability should be small. The probability should become smaller and smaller as we move away, as we get far away from the allowed region. The only allowed region in this problem is right here, where the position is 0, where it's only at this point that the energy is larger than the potential. So only at this point. So as we move far away in this negative direction, we need to have an exponential decay for the wave function. As we move far away in the positive direction, we need to have probability to find this particle decaying exponentially. All right, so in classically forbidden regions, we expect exponential decays of the wave function. All right, okay, so this is good because now we come back to our two equations and we already know what to expect. We expect exponential decays for these solutions. Well, let's now double check all that mathematically. Okay, so but our physics intuition is already there. So let's rewrite the equation for region 1 like this. I'm passing all the constants to the right side. All right, now, just as what we did for the infinite square, well, instead of keep writing this number 2, the mass, the energy, the h bar square, I'm going to try to substitute all of these symbols with a single symbol, but it's squared, okay? So this symbol, kappa, in our case, squared, is what I'm going to put on the right side of that equation. Well, mass, energy, h bar, these are all real numbers. So I'm going to put them all in a single symbol, square. This single symbol, squared, has to be positive. Okay, so I want us to decide now what we are going to include in our symbol squared. Okay, well, remember what we wrote. No? The energy is negative. So the only way to have something positive here is that we include also that minus sign. Yeah, because the energy is already negative. So if we include everything, including that minus sign, I can call this kappa squared. All right, so this is now the equation that we need to solve. Yeah? So we have equal to kappa square psi. What is the solution of this equation? Exponential, huh? Just as we were expecting. All right, so let's write the solution of this equation for this region 1. Minus kappa x plus b exponential plus kappa x. If you do the derivative, the second order derivative of this solution, of course, we are going to get to that equation above. Okay, so that's the solution. Very good, mathematically. But what did we say? We expect an exponential decay. Huh? And let's look at what we wrote here. This is the general solution, very good. But this piece here is problematic. We are on the negative side. This region 1 is the region for negative x. If I put negative value of x here, I don't know, minus 10, minus 100, minus 1 million, whatever you put here, we'll be dealing with an exponential that is positive, which will explode as we move further and further away, as we move towards minus infinity. So this is problematically. I cannot normalize a function that is exploding. So what we are going to do, even though mathematically this part is correct, we are going to get rid of this. So the solution that we have for the negative side is just this b exponential kappa x, because now we are very good. As I move to x very small, as this x goes to minus infinity, this will decay. I can normalize this function, so this is good. And what do we have on this negative side? Exponential decay. The further away I move from that position x0, the further away we go to minus infinity, smaller the probability to find the particle there. So things are going together with our discussions. Okay, so then let's keep this solution here. Let's now move to the other side, the positive side, which is also classically forbidden. It's the same equation. So if you rearrange, we are going to get the same equation as before. So I'm just going to copy it here. And the solution, again, is exponential. So the general solution for this region 2 is f exponential minus kappa x plus g exponential plus kappa x. And you see now which one of these, the solution is fine mathematically, but which one of these two parts is not good. No, it's not going to be considered because of the because we need to be able to normalize this function. So this is the part that will explode as x goes to larger and larger values. This part is growing exponentially. That's awful. We cannot normalize it. Now, remember the tails of the wave function, they have to go to 0. So we need to get rid of this part. Okay, so the only thing that survives, that is physically correct, is f exponential minus kappa x. Okay, so this is the solution. And this is good, goes with our expectations. Now we said, oh, it's classically forbidden. I do expect an exponential decay. As I move further away from the classically allowed region, which is right at x0, as I move away from that, entering this prohibited region classically, well, the probability to find the function, the particle there should decay. And on the negative side, this decay of the probability I can get by using the plus kappa x because x is negative. Okay, so there we are. We have these two solutions. Okay, very good. But there are many unknowns here that we need to find. We need to find B, we need to find F, we need to find kappa. Kappa is energy. Now is where energy is. So how are we going to continue from here? Well, now we are going to play with boundary conditions. The first thing that is important, that first property of these wave functions is that the wave function has to be continuous. Why? The probability square of the wave function is probability. It's what is going to give us the probability to find the particle here or there. So it has to be continuous. We don't want to see discontinuities in the probability. Okay, so it has to be continuous. So this is the first property. And if it has to be continuous, what does it mean? Where is the point where psi1 and psi2 meet, right at this position x0. So at that point, we have to guarantee that the wave function on the left side and on the right side, they match, they meet at the same point. Now, so we want to stitch these functions at that point. In other words, we want that solution that we found for the region 1 at position 0 to be equal to that solution that we found for region 2. Okay, what does it mean then? Well, exponential of 0 is 1. So from here, we find that B has to be equal to F. Ah, great. We got rid of one of the unknowns, F. And so what do we have now? So far, the solution for the equation, for the equation is B exponential of kappa x in the region where x is negative, and then b again, no, the f now is b, exponential minus kappa x when x is positive. Very good. Okay, now what is next? Well, we still need to find b and kappa. Now, kappa, again, related to energy. Well, we talked about one property, that the wave function has to be continuous. There is another property that we often find, well, in almost all cases, which is the derivative of the function also has to be continuous. Now, I said almost always because except in the problem that we have, except when the potential goes to infinity, okay? Except when, or let's put where, except where the potential is infinity. And that's exactly what we have in our problem at position 0. And so in many cases, you will see later when we talk about finite square well, barriers, many other problems, we do use this property that the wave function has to be, the derivative of the wave function has to be continuous at the point where two pieces meet, except where the potential is infinity, which is exactly what we have here. So we cannot use this very useful property. But we can still ask ourselves, what happens at that position 0 for the derivative? Okay, it's not continuous because we have an infinite potential, but what happens at that point where the two functions meet? Well, to study that, let's come back to the full Schrödinger's equation. Let me put here our potential. Okay, so this is the entire wave function. Let's try to play with this function. No, sorry. Let's try to play with this equation at the vicinity of x0, that point. Okay, so far, we never really took an advantage, we never saw the delta function at play. But right at x0, that's when the delta function has its an effect. So I'm looking at this equation, the Schrödinger's equation, and I want to study this equation very close to 0, at the vicinity of 0. So what I'm going to do is I'm going to integrate this whole equation at the vicinity of 0. Now, so this epsilon that I put, there is a tiny, tiny number, very, very close to 0. Negative on the negative side or very, very close to 0 on the positive side. Okay, so I'm going to use this integral in this whole equation. Huh? Okay, so let's now solve this integral. So on the first term, we have the integral of a second order derivative. So what is going to come out? Integral of a derivative. No? So if we have the integral of the derivative of a function, the solution is the function. So here we have the integral of the derivative of the derivative. So what is going to be the solution? The derivative. Okay, so that's what we are going to put. Here we are going to have the first order derivative now, right, when x is plus epsilon, tiny number, almost 0, minus the derivative, first order derivative, right at minus epsilon, tiny number, almost 0. Okay, very good. Second term, wow, second term, finally we see the delta function doing something in this problem. What is the solution when we have a delta function with a function? Provided that we involve the term from the delta function, and provided this integral, in our case, involves 0, we know that the solution will be the function right at 0. Okay, so that's what we are going to do for that term number 2. What is going to be the solution of this integral? It's going to be the function right at 0. Okay, and then the right side. Well, what is an integral? We are doing the integral of the wave function. What is an integral of a function? The integral of a function is the area underneath the function, correct? Well, now, what we are doing there is an integral. Yes, we are looking at the area, but tiny value. Yeah? So we have an integral for between minus epsilon and plus epsilon. So the area will be so small, because epsilon is an infinitesimal number. It's so small that I can say that my right side is practically 0. That area is practically 0. Okay, so very good. So now let's continue. Let's write here on the side what was the solution that we found, because we are going to need that now for the derivative. We said it's b exponential of kappa x for x negative, and it's b exponential of minus kappa x for x positive. Okay, so then, first derivative that we have is the derivative for the positive region. So I'm going to mark this. This is, I'm going to get that by doing the derivative from the positive side, okay? So it's minus kappa b exponential minus kappa at that tiny epsilon. Okay, the other one, the other derivative is for the negative. It's on the negative side, no? It's the minus epsilon. So we are going to be doing the derivative of this part. And what do we have? There is the minus that was already there. Kappa b exponential of kappa minus epsilon. Okay. Then we have minus alpha and the function at 0. The function at 0 is b, equal to 0. Well, why is it b? Because the function at 0, either piece that I select, is going to be exponential of 0, and the exponential of 0 is 1, so that's b. Okay, so now let's come back to our equation. Well, we are saying that this epsilon is practically 0, is infinitesimally small. So here again, we are looking at the exponential of 0. Okay, so I can say that this is practically 1. And this exponential is practically 1. Okay, so then what do we have? Minus h bar squared over 2m. And you see we have twice 2 kappa, so 2 kappa beta equals to alpha beta. Oh, beta, b, correct? All right. So now we can see we can simplify some terms. Now we have 2 and 2 here. We have this minus and this minus. We have b and b. So all that to finally conclude that kappa is m alpha over h bar squared. Very useful result, because remember, that was long ago, but remember that kappa square is all this. Kappa square is where the energy is. So I'm going to even copy this and bring down. So there we are. Kappa square is related to the energy. So if I found kappa, now I can then find energy. The energy is minus h bar square kappa square over 2m. So then we conclude that the energy is minus h bar square kappa square m square alpha square h bar to the 4th, and there is also this 2m. It cancel this m. Here we can get rid of this h bar square. So then we found energy now is minus m alpha square to h bar square. Very good. We got the energy on the problem. And you see the minus sign there, because we started from this assumption. We were playing with these bound states, energy negative. Okay, so we got the energy. We are almost done. What is missing in this story? Well, let's have a look at what we wrote for the wave function. We have this. So what is missing is B. We already found everything. We found the energy, we found the solution, but we still don't know what B is. It's the only last thing for us to do. It's the last unknown. And when we have just one last thing, what do we resort to? Normalization. Yeah. So let's go. We know that the wave function has to be normalized. We know that this integral from minus infinity to infinity has to be 1. And from there, we are going to get what B is. Okay. The solution has 2 pieces, now for the negative and the positive sign. So I'm going to write the integral from minus infinity to 0. And I pick this solution here. So we have absolute value of B squared, exponential squared, so 2 kappa x. And the other part, from 0 to infinity, B squared, absolute value of B squared. Then we have the exponential minus 2 kappa x, because now we are talking about positive x. That's what we need to solve. Okay, so then we have b squared exponential 2 kappa x divided by 2 kappa. That's the solution of that integral in this range. Plus b squared, the solution of the integral is, again, this minus 2 kappa x now with minus 2 kappa, 0 to infinity. Okay. Now, what do we have here? I'm going to write, it doesn't hurt. So we are talking about, let me put this 2 kappa out, exponential of 2 kappa at 0 minus exponential of 2 kappa minus infinity. Okay, and the other part is exponential minus 2 kappa at infinity minus, there is this term that I should not forget, minus exponential minus 2 kappa 0. Well, exponential going to minus infinity is 0. Okay, exponential here going to minus infinity is 0. Okay, so this is 0, this is 0. Exponential of 0 is 1. Same thing here. Exponential of 0 is 1. Okay, so putting all this together, we have b squared 2 kappa. From the first term, I just have number 1. From the second term, careful, we have a minus here and a minus here, so plus 1. Okay, so then we got b squared over kappa is equal to 1. All that to tell us b is the square root of kappa. And we know what kappa is. We found it above. Is m alpha, so square root of that. In the denominator, we had h bar squared, so h bar. So for you to see it again, here, oops, here. So I did the square root of that. All right, so now we have everything. Let's put everything together. We have the solution, the wave function is, in the place of b, we are going to put the square root of kappa. So square root of m alpha and then the h bar, exponential of kappa, but now we know what kappa is. So m alpha x over h bar square. This is on the negative side. On the positive side, minus m alpha x over h bar square on the positive side. And the energy for this bound state, we have just one value of energy. So that means we have just one bound state. What is the energy of this single one bound state that we found? Negative, minus m alpha square over 2 h bar square. So this is the solution for the energy. This is the state that we found, the wave function. If you want, you can write this solution here in a more compact way. You can write it in a more compact way like this. Now, in the exponential, to include both parts, the negative and the positive parts, you can write it with an absolute value. That way, you include both. Okay, so this is, but it's okay if you prefer to write in this long form, it's fine. Now, but what we have then, the energy, and this is the solution, the wave function. And that's it for the negative energy, for the bound state. What we are going to see in the next video is the case where the energy is positive, which gives us scattering states. Okay, so that's it.